Good. It's recording.
Thank you very much, and thank you very much for inviting me to give a talk. I've thoroughly enjoyed some of the talks that I've been able to listen to, and so it's a great pleasure to be able to share some of the thoughts and work that we do here at the University of Warwick. So I thought I'd start with sort of setting out the question that I'm going to try and answer, or at least talk about in today's lecture. And that's really about how we in the academic community can try and support rapid development and adoption of new steels and indeed processes. And clearly this requires innovation and thinking. And we should not be constrained by current capabilities in that innovation and thinking. But sometimes if we want to ensure that we have some rapid adoption or more rapid adoption, it's appreciating some of the industrial constraints and process sensitivities so that we can develop some of the new steels and ideally see them adopted and being used. As a starting point, I wanted to just refresh for those who may not be so familiar with the steel process, some of the key microstructural developments that occur during industrial processing, and what we need to do to take these into account when we consider how to develop improved steels or indeed new concept steels. So I'm taking as an example, particularly dual phase and complex phase steels as I go through the talk. But I'll start off with sort of the generic strip steel production route and some of the considerations. So we start at the casting stage. Then from a microstructural point of view, I'm very much going to focus on microstructural developments as we go through processes. And from a microstructural viewpoint, we need to be aware and take into account the effective cooling rate, which of course depend upon the casting technique that is being used, and the composition of our steel for the microstructural development, and particularly the aspect of the microstructure that will affect subsequent microstructural transformations or formations, which will be segregation. So here we have an example of a as-cast slab microstructure where the perlite is showing the remnants of the as-cast microstructure through the dendritic solidification, because the carbon will be co-located with the interdendritic segregation behavior. And from this, we can also then get an idea of the scale of the inhomogeneity by looking at secondary dendrite arm spaces. We move on to the reheating stage, and this is where we reheat and get an austenitic microstructure, and ideally we want to have a homogeneous, reasonably uniform grain size. This is just a quenched sample that's been etched to show the pyroxite grain boundaries. And during this reheating stage, we need to consider aspects such as the grain growth, and not just average grain sizes, but actually grain size distributions, because they will have knock-on effects during subsequent processing. Or we might need to be considering things like the precipitate dissolution. And obviously with precipitates, we need to consider that local composition which comes from segregation behaviors. Moving on to the hot rolling process, then the microstructural phenomena that tend to be occurring here are things like recrystallization or rolling below the non-recrystallization temperature and getting a pancake grains where our austenite grains become elongated. We get phase transformation on cooling. We'll have potentially a banded microstructure because of the segregation behavior. And we need to consider the grain size and indeed precipitation that's going on during that process. Our cold rolled microstructure, subsequent to this, we have a high dislocation density or stored energy depending on the amount of cold reduction that's put in. We get quite a different grain shape because the ferritic grains, second phase grains get highly elongated and deformed. And we potentially could be generating quite strong crystallographic textures that will have implications later on for properties. And then in many of these, and particularly for some of the dual phase steels that I'm going to be talking about later, we have annealing, generally through continuous annealing, And again, we've got a whole load more microstructural developments that we need to take into account. Again, recrystallization from this cold work microstructure, potential changes in phase balance of particular relevance when I'm talking about dual phase steels. We're going to have the grain size, and this will be now getting to our final grain size, which will be controlling our mechanical properties. Again, the crystallographic texture and potential for precipitation at this point in the development as well. So for steels, we're blessed and we're very lucky that we have so many process stages and so many microstructural changes. It gives us huge scope for getting advanced materials. But we're also burdened by the fact we have to take all of these things into account if we're trying to develop something that's new. So when it comes to our dual phase steels, I've just summarized what I've been talking about, but there's a lot of considerations. And the approach to being able to, one, understand how each of these stages affects the development of the microstructure for dual phase steels, and then to consider if we want to make improved materials, how we ensure that we achieve what we want to through all of those stages. We can use a combination of both modeling and experimental investigations. And I'd also like to highlight the increasing use of in-situ observations, which really can help understand each of these microstructural developments. So let's start back at the casting point to understand the microstructures that develop. So here we've got some micrest simulations going. On the far left-hand side, the little video there is showing the microstructure from the initial solidification of dendrites and then transformation to an austenitic structure. On the far right-hand side, it's the same microstructure, but now rather than showing the dendrites, etc., we're showing compositional variability, here looking at manganese. And what we find is that you get this dendritic structure, you get the interdendritic segregation, at the moment we're just highlighting the manganese, and then post-solidification, you get back diffusion, and so it softens the segregated composition that's going on. And so we've got some very nice tools to be able to simulate the process. We also want to make sure that our simulations are grounded in experimental evidence. So here's one of the first examples, a very nice example of in-situ observations that can help verify some of the modeling approaches. This is imaging from a confocal laser scanning microscope, where we're looking at the surface of a liquid steel as it goes through solidification. I think it's fantastic you can actually see steel during solidification. Here we can see the dendritic structure. When this loops back, you'll see the dendrites that start to form. So careful cooling considerations. So in this case, the dendrites are growing almost parallel to the surface of the liquid steel. So that example there shows very nicely the primary dendrite and secondary dendrite arms. And from this type of observation, we can see boundary velocities. We can link those back to compositions, cooling rates, and we can also use this to subsequently verify for secondary dendrite arm spacings and indeed for segregation levels. And we've been very careful to make sure that we correlate the surface observations with bulk observations as well. Whenever we look at surfaces, we do have to be a little bit careful as whether we're getting surface effects, but actually in this case, there aren't too many surface effects. And the thing you might have noticed just at the end of the video, before it looped back, is at the end of solidification, we get then the transformation to the austenite, and actually you can see the austenite grain boundaries. And should we continue with this, you can see the austenite grain growth, and that's the thermal etching effect. So just here, we can see some of those boundaries. All of this is really important to build up some of the relationships. Here I've just shown a relatively simple empirical relationship between secondary dendrite arm spacing and cooling rate. I've got some examples here from some stainless steels because we related that to prior literature as well. Also looking here for a low density steel, and I have data, but I don't show it here, for dual phase steels and carbon manganese steels. And what's clear is that there's quite a definite relationship between the secondary dendrite arm spacing and the cooling rate. Now, why is that important? That's particularly important because it also then affects the spatial distribution for composition. So on the right-hand side, I show a graph, in this particular case, niobium content, but we can do it for manganese, we can do it for chromium, we can do it for whichever alloy element we want, to show both this spatial distribution, that's the secondary dendrite arm spacing length, and the magnitude of the micro-segregation, this is interdendritic segregation. And here we can see that as you go to faster cooling rates, so the 50 degrees per second, you have a much sharper segregation profile, but over a much finer length scale. And that's simply because there's less time at temperature for back diffusion to soften that segregation profile. Of course, if we have reheating, then we can soften it during the reheating process. But still, why is this particularly relevant and important? Because it has knock-on consequences for later microstructural development. And I thought I'd show that these features are really important for a product as well as just in the lab. Here's an example of a steel plate, and it's actually a really old micrograph that's 15, 20 years old. But I think it's quite nice to show that even though our characterizations improve, that some of the principles are exactly the same, that the science doesn't change. What I have here is niobium carbonitride microalloy precipitates, and actually you can separate it into two very distinct regions in this microstructure. Where we have some of the pearlite, then you can see a much higher number density and larger size of these niobium carbonitride microalloy precipitates, and that's because the pearlite corresponds to the interdendritic solute rich regions. And in the blue highlighted box, there's actually very few precipitates that are present, and that would be corresponding to the dendritic area. So we get this spatial distribution in terms of composition, and the spatial distribution can then affect our behaviors and properties. And so this all links back to what's happening in the cast material. Well, what about when we come on to reheating? During the reheating stage, we're typically taking the material up to around 1200 degrees Celsius. If we have alloying elements, microalloying elements such as niobium in there, generally we're trying to get things back into solution so that they can then affect the microstructural development during hot rolling. And we have significant grain growth, and we tend to start with quite a coarse microstructure. But there are several phenomena that can, not always, but can occur during the reheat process. What we want to achieve is a uniform grain structure with our microalloying elements back in solution, if we're talking about something like niobium. However, there are phenomena such as abnormal grain growth and the bimodal grain growth that can occur. One of the things that we've looked at in the past is when and what conditions do you get these phenomena. Abnormal grain growth tends to occur where you're very close to the dissolution temperature for pinning precipitates. And so you get a few local regions where precipitates dissolve and those grains suddenly become released from their pinning, and you get this very large grain growth. And you can see on that bottom left image, grains that suddenly become hundreds and hundreds of microns. And indeed, you can see examples where austenitic grains have grown to millimeters in size. And it's quite difficult to refine them during subsequent hot rolling. So if they occur, they affect the final product properties. What we've found is that actually it's quite hard to make some of the steels, commercial as cast slab steel, go to an abnormal grain structure. What we found is that you tend to end up with a bimodal grain structure because you've got this spatial distribution of precipitates, then in the dendritic regions, where you have a lower concentration of microalloy elements, the precipitates dissolve first. And so indeed the grains do start to grow, and you'll get a few that will really start to grow. But because you have the interdendritic regions with the higher solute content, those precipitates are thermodynamically more stable. And so they pin those larger the growing grains. And so you restrict the size of the larger grains that form. And you end up with this slightly more bimodal, where almost running sort of bottom left or top right of the graph, of the image rather, you can see the larger grains. And then next to that, you've got much finer grains. One thing that we did find that was very interesting, it comes back to this understanding the difference between what we do in the lab and what happens in industry, is that we took rolled material. So in other words, we reduced the separation between the solute rich and the solute poor, such that you had a very, very fine spacing, talking about 10 microns or less. And carried out reheating trials there, we actually found we could make the material show abnormal grain growth, because now when the grain started to grow, they had enough driving force, because it behaved almost as a homogeneous material, because the length scales between any of the segregated regions were very much finer. So one of the things that we know is that ensuring we avoid these non-uniform grain structures, we do need to take into account what's happening in a representative as cast microstructure, not always just a lab microstructure. Then coming down to rolling, then hot rolling, taking that as our starting point, will reduce the thickness of the as cast slab to the hot rolled strip thickness. And our typical microstructures that we see are these banded ferrite perlites. If we're talking about DP type steel composition, then we have these banded ferrite perlite microstructures. And the bands and the band spacing, linked back to the micro segregation, is important because it affects, for example, ferrite grain size, because you have pinning points. It affects the properties of the material. So in the lab, if we're trying to replicate a commercial hot rolled material, we need to make sure that we replicate the band spacing appropriately. The modeling approach that we take to that is to consider the lab scale ingots that we cast. Here in Warwick, we have a VIM. We typically cast around about 7 to 8 kilo into molds, although we're now we've got capability to go up to 15 kilos or more. But we look at the size of the molds that we use, and in the graphs I show examples of 10 to 50 millimeter width mold sizes. Model those for thermal transfer so we can understand the cooling rates, carry out lab experiments to make sure we can verify that to get the secondary dendrite arm spacings. And so the bottom left graph there shows the secondary dendrite arm spacing for a DP steel, in this case, for different mold thicknesses. So in other words, our cast ingot. Then if we're going to roll this down to 1 millimeter, at the moment, that's the thickness that we've chosen, then we know what our rolling reduction is. We know our starting secondary dendrite arm spacing. We can see what secondary dendrite arm spacing we would have in that rolled product. And by looking at commercial material, we can make sure that we select the appropriate ingot width and rolling reduction to give something that's representative of commercial material. And then we can ensure that we're replicating the microstructural developments as we go through. Whilst talking about hot rolling, I also ought to mention about the importance of our experimental simulation behavior and understanding that, particularly when looking at microstructures, and that's where our focus is today. So for lab behaviors, we can have lab hot rolling. one of the challenges is maintaining the temperature as we go to smaller samples when we do our laboratory hot rolling. And particularly if we're looking for the control for the strain and temperatures and interpass times, it can be challenging in a lab mill. Ideally, we can get that optimized, but quite often we might want to be looking at using thermomechanical simulation to get our microstructural behaviors or indeed recrystallization kinetics. There's a number of approaches that can be used, from uniaxial compression, plane strain compression, torsion testing, and they all have different strengths and challenges in order to understand microstructural development. And I've just shown one example here that we've focused on, the difference between a uniaxial compression sample on the left-hand side and a plane strain compression sample on the right-hand side for the volume of the sample that has a desired strain for looking at the microstructures. So these are two simulations that have been carried out for the same macroscopic strain, which is 0.3, and then mapping where in that sample a strain of 0.3 is actually experienced. And we can see that in both cases, we've got significant strain gradients. But on the right-hand side, there's larger area, if we select appropriately, that has a uniform strain of 0.3. And this is important if we're looking at full microstructural development and grain size distributions to ensure that we are able to correlate it directly with the exact values of strain. Also, when thinking about processing, we have strain variation through thickness. In the labs, we tend to use smaller samples, and we need to be aware and conscious of strain and temperature variations. And so therefore we can map the microstructural development through an entire product thickness. When we start to go to very thin products, such as some of the strip, actually a lot of the behaviors for thin strip start to become very similar because you recrystallize repeatedly down to a similar grain size, for example. But thicker product and these temperature and strain gradients become particularly significant. So we need to be conscious of that in how we replicate behaviors. And indeed, thinking about, again, focus on microstructural development and how this behaves. The little video there in the top left is showing thermodynamic mechanical simulation. Here we have it's a global thermomechanical simulator, but it's a slightly different one than the very familiar ones, the 3800s. This one's called an HDS system, where the anvils are separated from the heating elements, and we can have very rapid multi-hit deformations. And then the little video on the right-hand side shows how we can couple the understanding of the strain and the temperature history to our microstructural development, here showing a grain size distribution. And during the deformation hits, you get the recrystallization, so the much finer grain size. But we know that the finer grains recrystallize quicker than the coarser grains. I'll show some reasons for that in a moment. And so you can start to see this shift in our grain size distribution, and the fact that it's not a immediate change to a finer grain size, but you actually sort of get that partial recrystallization, and then that sweeps through and you can get the recrystallized grain size. And so mapping both the predictive capability, and indeed there's still plenty of work that needs to be done to ensure that we can replicate full grain size distributions. We're coming back to one of the principles that I mentioned to start with, which was about how we take into account all the stages of processing. Then I wanted to highlight an example where segregation behavior affects our recrystallization behavior during hot rolling, and again, that appreciation. So this is a little example showing a carbon manganese steel. And we have two samples, the same material, cast the same. So we have a segregated composition. So these are XRF maps over about a 6mm square surface region, showing the manganese levels. And bottom right, you can see the strong banded segregation of manganese. And then we've done some repeated heat treatments to homogenize the sample. And so the sample on the bottom left is the same material, but now being homogenized. You can still see the remnants of the segregation, but it's much, much lower. And if you look at the range of values, we've been able to homogenize it quite well. What we've looked at is the recrystallization behavior when at, in this case, 900 degrees Celsius, so it's fully austenitic. So there's no differences in grain size. So we ensured that we've heat treated it to get the same pyroxenite grain size. Only difference between these two is one has the segregated manganese distribution, the other one is a much more homogeneous. So the bottom left graph here shows an interrupted test where it's been deformed to 0.3 strain, held for 30 seconds and then quenched to show how the grain size develops. And in this particular case, the homogenized material is fully recrystallized, which is actually what we would predict by using the average composition, starting austenite grain size and strain from the equations that are in the literature, the Dusser-Sellers type equations. But interestingly, same conditions, the segregated material is only partially recrystallized. And I want to emphasize they did have exactly the same starting austenite grain size. So we've got a difference in the recrystallization kinetics. And actually even more interesting, for me, is the fact that after full recrystallization, which is the graph on the bottom right, we still have a difference in the austenite grain size. And the segregated sample has a slightly wider range and a larger mode grain size. In order to understand this, so we can be predictive about it, what we've done is taken the XRF compositional map and used that to determine the local flow stress of the material, just by using the equations for solid solution strengthening. And then taken the local flow stress behavior and put that into an FE model to consider the macroscopic deformation. So one of the models from the plane strain compression test or uniaxial compression test, whichever we want to look at. Deformed the two with a more homogeneous composition and the segregated microstructure to the same strain, to the 0.3 strain, and then plotted out the local strain distribution. And what we can clearly see is, and it's not a surprise, it's what we'd expect, but even for that small difference in local composition for manganese and just solid solution strengthening, you get strain partitioning. And that strain partitioning is sufficient to give you that differences in recrystallization kinetics and indeed the recrystallized grain size, albeit just for one deformation cycle. So again, these things become quite important to be able to have that flow through the process of our microstructural development. A little bit for the in-situ observations. Here's an example, again, particularly important here for us was looking at how the grain size distribution develops during deformation. And so these are in-situ EBSD maps, being able to look at the, follow the process of recrystallization. So the top left image here is showing basically the strain distribution, and what being able to illustrate is the variation in local strain based here just on grain size. So smaller grains tend to accommodate a higher strain, so you have a high dislocation density. And then we can see through the formation of the recrystallized grains, so these are taken up, heated, held for a little bit of time, and then EBSE, you can follow the recrystallization process and the recrystallization happening in the highly strained areas, again, not a surprise. But it illustrates to us the importance of what your starting grain size distribution, not just the mode grain size, particularly when we start to get skewed distributions. So these more complex steels where we might not have a very tight unimodal grain size distribution. So really important to understanding principles of what's going on as well as some of the data. Moving on, we finish our hot rolling process and cool the material down to room temperature, cool to a coiling temperature, and have microstructural transformations. So for my example of DP steels, here if we're going to be cooling, we'll end up with a ferrite perlite microstructure typically. There are some DP steels that actually have some bainites in them as a starting point. But here, if we have a ferrite perlite steel, and actually the cooling rate after the hot rolling process and the pyroxenite grain size will affect the ferrite grain size. Pyroxenite grain size is really straightforward, but the ferrite grain size being affected also by the cooling rate, and that becomes important to appreciate for a given industrial process. What is the run-out table and the cooling configurations? What is the coiling temperature as well, and the balance between the nucleation and growth of our ferrite grains from our austenite, and indeed some of the preconditioning of the austenite if we have any rolling below the recrystallization stop temperature. A little bit more about in situ monitoring. This is slightly less direct, but it's still a very good example for phase transformation monitoring. This is some of the work that we do in the group using electromagnetic sensors. Here's an example of a sensor that's fitted into a run-out table for a hot strip mill. Bottom left shows the FE models that we're able to give you the predictive. And really what we're doing here is looking at monitoring phase transformation during cooling, because we want to ensure that the predictive approach using, for example, CCT curves, so what temperatures and what cooling rates we need to optimize our ferrite grain size, how that relates in practice. And then I've got some examples. These are from our lab, but you get certain data points from the industrial application. Really here, I've got data for changing the thickness of the strip. That correlates to a difference in the cooling rates, and that affects the transformation temperature. And we can see here that the sensor signal, which is what's called the zero crossing frequency in this case, plotted against temperature. But above 770, we have a flat line because our material is not magnetic, so we get no signal at all. But post or below the Curie temperature, we get to see the effect of cooling rates and strip thicknesses on where the transformations occur, and therefore the signals. So it gives us a slightly indirect measurement, but it's directly linked to the microstructure and the phases that form and providing interesting information. So this is some of the work that we do in our lab, but actually I'm really excited that there's quite a lot of new in situ microstructural measurement techniques that are coming online for industrial application based on X-rays or ultrasonic measurements as well. So I think it's really quite an exciting time for being able to do much more in situ measurements, in particular during industrial processing, not just in the labs. Following my journey through the processing route, let's move on to the cold rolling and annealing stages. The cold rolling is predominantly there to result in the required thickness for customers want for our strip, but it also will give us different cold rolling reductions, therefore different stored energies in our strip that will drive the microstructural development processes during annealing. And it's important to look at the sensitivities to the different processing parameters for final product. So what I've got here is an example of that process sensitivities, because generally speaking, we'll even for a single composition, single property range DP steel, there may be requirements for different thicknesses. And so we need to be able to try and make those different thicknesses with consistent properties. So this graph is showing the martensite fraction in a DP 800 material for the same heating rate, in this case, the same peak temperature, but for different cold rolling reductions. And what we see is that if we're going down to relatively low cold rolling reductions, 45% in this case, which is a commercially used cold rolling reduction, we can start to see quite strong sensitivity to the microstructure that's developed, whereas above the 60 to 75% cold rolling reductions, we don't see that. The reason for that is because of the stored energy and the driving force for recrystallization compared to austenitization. When we have the higher cold rolling reductions, we have greater stored energy, but the driving force for recrystallization, and recrystallization happens before the austenitization process. That isn't the case with the lower cold rolling reduction, so we get a difference in that balance of the austenitization and therefore the martensite fraction that is formed. We also see a similar principle, but now keeping the same cold rolling reduction. Here I've got 75% cold rolling reduction, the same peak temperature, but if we change the heating rate, of course, different annealing lines, different product thicknesses in terms of line speed will give different heating rates. And here we can start to see there is also sensitivity. And I think this is, for me, this has been quite an interesting exercise, is to understand more about ensuring steels that we wish to develop are robust against the typical ranges of process parameters, not just a set value that we might choose to use in the lab. So I put the groundwork in place to say these are some, I haven't covered everything, but these are some of the key parameters we need to consider when we start to develop new steels or try and improve existing steels. And the way that this is done is through rapid alloy prototyping. And there's a lot of labs and fantastic work being done all around the world on using the sort of the rapid alloy prototyping approach. And we see different types of approaches depending on what type of metal or processing that is required. So high entropy alloys, fantastic, using lots of different sort of compositional matrices and then maybe the heat treatments to understand the different properties. Some grades of steel that may get most of their properties from final heat treatments, such as some of the quenched and tempered, and it's compositionally done, we can look at compositional matrices. But I think for some of the grades, like the dual phase steels that we're talking about here in strip, we actually do need to consider through process when we go through those developments. So our rapid alloy prototyping, very similar to many that are available, and it needs this careful consideration of each of these processing steps to make sure that we replicate the important features from production that we want to ensure we consider. So we don't have to consider everything for every grade, but for some we certainly do. So we had a thought exercise and a name, which was to develop a new DP 800 grade, but to develop a grade that potentially could be adopted using conventional DP steel processing routes. Also, we thought we'll make life difficult for ourselves and try and ensure that this could potentially be done in an economic way. So not putting in lots of additional processing steps. There's some really nice work that people have done using additional heat treatment cycles to improve and give high ductility DP steels. We said, no, let's see if we can achieve something without doing that and without making it too expensive from a compositional. viewpoint. So our aim was a new, different DP formulation. And in particular, we wanted to have reduced mechanical property anisotropy and enhanced ductility. That was our requirement. And to do that, we said, right, we want to try and achieve something that doesn't have this banded microstructure, because that banded microstructure gives anisotropy in the mechanical properties. We know that the banding comes because of the segregation, and segregation comes because of the casting and our secondary dendrite arm spacings, etc. So we wanted to neutralize the segregation that happened during casting. And to achieve that, the principle was then to use sort of co-segregation of both austenite and ferrite stabilizers, so that we didn't end up with the conventional manganese-rich areas. They are the austenite stabilizers, therefore that's the last austenite that transforms. It's got carbon in it, so you get the banded austenitic structure. So our principle was to try and avoid that, that process. But we also needed to maintain our strength levels. So we've got to think about keeping the same amount of second phase, maintaining grain size. And if we're going to change the composition, do we still have the same amount of solid solution strengthening? So quite a few things to consider. So one part of it was the solid solution strengthening. So we mapped the most significant solid solution strengthening elements. So not everything, but just taking this as a nice simple 2D example, where manganese is the dominant solid solution strengthening element in our current composition. We were looking at silicon as being a good solid solution strengthening alternative at low cost. And so we can map on a heat map and look to see where we would need to be to have similar solid solution strengthening. And then we said, right, we want to minimize our segregation. So we want to minimize the difference in the AU1 temperatures between the solute-rich interdendritic, solute or dendritic regions. So things like thermocalc to predict what those temperatures are based on our known segregation behaviors. So for example, the micrest behavior. And we can say, right, where we start from, we actually have a difference in those temperatures of around 50 degrees. And that's why you get this strong segregation behavior. But if we want to minimize it, then where do we need to go? So we want to get this down to around 10 or less than 10 degrees, because then we shouldn't get that strong preferential carbon diffusion into manganese-rich areas. But we also link that back to our need for solid solution strengthening. So I mapped the two things together, we can come up with a proposed composition. So that's our principle, design principle for the two particular elements that we were looking at. So we carried out the same processing in the lab. We benchmarked our lab processing for the conventional composition against commercial material. That's the image on the bottom left, very familiar. Banded ferrite martensite, ferrite perlite in the hot rolled condition, microstructure. And what we found is that when we've taken our design principle to neutralize that segregation behavior, then we no longer have the second phase being in the manganese-rich areas. We now have nucleation and formation sort of on triple points during the annealing cycle, and therefore you get a more random distribution, and indeed that's what we see. So far so good. We've also then done a little bit more in-depth analysis just to say, is this because our design principles were working? So here we've got some EDX line scans over the conventional material. And the most important thing is you can see that the manganese content shows a spatial distribution, and the peaks in that distribution pretty much all line up with martensitic regions. You do get some martensite without a peak, simply because there's more martensite in this DP800 than there are the interdendritic segregation rich regions, but where you've got a peak, you have got martensite. And interestingly, for this segregation neutralized DP steel, then we see much lower manganese levels, because we had purposefully taken out manganese, but we see peaks both in martensite and in ferrite. So there's no preferential phase distribution within these two regions. So it looks like we're achieving what we set out to do. And then one of the other things, again, for some of this, looking at how we map these to properties, and this is the part we're just starting to use for this material, is to start to look at that three-dimensional distribution. But when it comes to mechanical properties, there's actually 3 dimensions that we need to worry about. We've certainly been able to see a reduction in the banding in the 2 dimensions, and we look at it on each of the sections for our strip material. But what we want to do next is start to develop our 3-dimensional mapping. So here's an example of using focused iron beam fib lift sectioning in the SEM and then the EBSD data. This is a volume of about 50 microns by 20 microns by 15 microns at the moment. And so we're just starting to do that, and we want to link this then through to mechanical properties to see how the spatial distribution will directly link to anisotropy. That's work in progress. But I did say how important it was for us to consider our process sensitivities. And so here's an example of where we've taken the results that I showed before, the commercial DP material, and its sensitivity for a given set of reheat conditions to the cold rolling reduction. We've done the same thing for the segregation neutralized DP steel, and we see much less sensitivity. Now, I have to be a little bit careful. That's because the oscillation temperature is much higher because of the change in composition. So we do have to reheat to a high, or anneal at a higher temperature. So there is more thermal drive for recrystallization before you start to get the oscillation. But that's okay. So at least we've got that understanding in place. And so some of this would then need to be mapped against annealing temperature capability as well. But we're starting to get an appreciation, and fortunately, it's worked out with less sensitivity. But we have other considerations. And then, have we achieved what we've set out to achieve? I can't tell you 100%, but I think we're looking good. I don't have the final annealed martensite, ferrite martensite data yet, but we do have the hot rolled conditions. This is still looking at the differences of whether you have a banded or a non-banded microstructure. And we can see that in the standard benchmark material that you do have significant anisotropy depending on the orientation that you take your test from, which we expect because it's a banded ferrite perlite steel. And when we have a more homogeneous distribution of second phase, we end up with a much more uniform behavior in terms of the orientation effects. And so it's a watch this space to make sure that we achieve what we set out to achieve for the ferrite martensite steel as a result. And of course, I think this is a good step forward in terms of trying to consider each of the aspects as we go through, but it's not there yet. There's so many other things that need to be considered and are starting to be considered, but the oxidation behavior, because we quite significantly changed the manganese silicon ratios in these steels. And this is not necessarily a final compositional mix, but certainly moving towards that way. We haven't done the full range of mechanical properties on the final product. And of course, there's things like the weldability that would need to be considered. So it's always a little bit more complicated than you would hope when you sit down and try and develop something afresh. But I hope what I've shown is that the use of rapid alloy prototyping coupled with modeling and simulation allows us to do that innovation and thinking. And I've tried to pick out one example to illustrate the process, and there are lots of other examples that we've done. There's lots of really good examples from other labs across Europe, across the world. And really, I think that my final point is that it's brilliant to do this, and it's really important, and it's nice, and it's even better if, as my daughter would say, even better if we can take into account some of the industrial considerations and sensitivities as we go through the thought process. Even if we want to say we've considered them and then thrown them out the window because we want to do something that's really different, that's okay, as long as we can say that that's what we're trying to do. And so I'll finish the talk by really saying a huge thank you to those whose work I've included in this talk, who I've listed here, but actually to the much wider group that I'm very fortunate to work with in the steel group at WMG. Thank you very much.
Thank you very much, Claire, for a wonderful presentation. It shows very nicely all the challenges that we have to face when we want to process the steel on an industrial scale, and yeah, the enormous complexity. And yeah, I must congratulate you with being able to, design a steel as this segregation neutralized steel, as you called it, and manage to in that way get rid of the bending and reduce the anisotropy. It's really a nice example of how to combine scientific insight and experiments. Let me stop the recording, and then we can start with the discussion.